Hello everyone, myself Kirti. I'm a student of BSc Chemistry Honors final year. This is an audio recorded lecture on the topic Physical Properties and Molecular Structure from Physical Chemistry. This is Pradeep's publications and the author of this book is Dr. S.C. Khetarpal. So let's start the chapter. Introduction. The various methods used for the study of molecular structures may be broadly classified into the following two types. First, methods based upon the study of physical properties of the substances such as molar refraction, optical activity, magnetic susceptibility, paracore and dipole moment, etc. Second type is spectroscopic methods such as rotational and vibrational spectroscopy, electronic spectroscopy, Raman spectroscopy, nuclear magnetic resonance spectroscopy, etc. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as that property that the total value of which is the sum of the value of its constituent atoms. And a constitutive property of a molecule is defined as that property which depends upon the constitution of the molecule, that is, arrangement of atoms within the molecule and the presence of multiple bonds, rings, etc. in the molecule. Spectroscopic methods have already been discussed. Now, in this chapter, we shall take up a brief discussion of three important physical properties, namely optical activity, dipole moment, and magnetic susceptibility, one by one. So, first, we will start with optical activity. Definitions. Plane polarized light. If a ray of light travel in any direction, it has vibrations in all directions at right angle to the path of propagation. If the light is passed through nickel prism, then the light which emerges out of the prism is found to have vibrations only in one plane. This light is called plane polarized light. The nickel prism thus used is called a polarizer. Second property is of optical activity. If the plane polarized light is passed through a plate of quartz or the solution of sugar, it is found that in the light that comes out, the plane of the polarized light gets rotated. The substance like quartz, sugar, etc., which rotate the plane of the polarized light are called optically active substances, and the property of a substance to rotate the plane of the polarized light is called optical activity. The substances which rotate the plane of the polarized light to the right are called dextrorotatory, and those which rotate the plane of the polarized light to the left are called levolotatory. The method of observing the rotation of the plane of the polarized light is based upon the following principle. If the plane polarized light is passed through another nickel prism which has its axis parallel to that of the first nickel prism, the light passes through and brightness is observed through the eyepiece. On the other hand, if the second nickel prism is placed with its axis at right angle to that of the first prism, the light is completely cut off and field of view in the eyepiece is dark. At all other positions, the brightness is less, but there may not be complete darkness. It is observed that if the two nickel prisms are set at the crossed position so that the field of the view is completely dark, and then the optically active substance is placed between the two prisms, the field of the view becomes somewhat bright. The second prism has to be rotated through certain angle about the line of propagation of light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of the polarized light has been rotated. The degree of rotation depends upon the rotation required to be given to the second nickel prism to get the darkness again. Thus, just as the first prism polarizes the light and is called polarizer, the second prism analyzes the light and is called analyzer. This is the diagram which shows the principle of observing the rotation of the plane of polarized light. Third definition is of specific rotation. The angle through which the plane of the polarized light is rotated on passing through the solution of an optically active substance depends upon the following factors: nature of the optically active substance, concentration of the solution, length of the solution, wavelength of the light used, and temperature of the solution. Thus, if m grams of the substance are dissolved in V milliliter of the solution, and L is the length of the tube, and x is the angle of rotation, then it is found that alpha is directly proportional to the concentration and length. So this is the derivation. Now, if m is equal to 1 gram, volume is 1 milliliter, and length is 1, then alpha is equal to alpha. Hence, specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance is dissolved in 1 milliliter of the solution. In all reported values of alpha from lambda to T, the concentration of the solution is taken in grams per 100 milliliter of the solution. Thus, if C grams are dissolved in 100 milliliter of the solution, then we may put M is equal to C and V is equal to 100. This gives the equation alpha limits tends from lambda to T is equal to 100 into alpha divided by L into C for solutions. Further, if instead of solution substance taken is a pure liquid or a solid, then M by V is replaced by density D of the pure substance. This gives the equation alpha limits tends from alpha to T is equal to alpha divided by L into D for pure liquids or solids. Fourth definition is of molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight m of the substance and dividing the result by 100. It is usually represented as m limits tends from lambda to T. Next is measurement of optical activity. The instrument used for the measurement of the amount of rotation caused by an optically active substance to the plane of the polarized light is called a polarimeter. The principle of this instrument has been already discussed. It consists essentially of two nickel prisms, one called the polarizer and another one is called the analyzer. Both of these are fitted on the opposite ends of the same metal tube. However, the polarizer is fixed, but the analyzer can be rotated about the axis of the tube. In between the polarizer and the analyzer, there is a space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 cm or 25 cm and has glass windows on both ends. A circular scale is fixed on the metal tube near the analyzer as shown in the diagram. In the procedure, first of all, monochromatic light from a suitable source is passed through the instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of the view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution is placed and the shutter is closed. On seeing through the eyepiece, the field of the view is no longer found to be dark. The analyzer is rotated slowly till the field of the view is completely dark again. This gives the final reading. The difference between the final reading and the initial reading gives the angle of rotation alpha. If it comes out to be positive, the substance is dextrorotatory, and if it comes out to be negative, then the substance is levorotatory. Modern instruments have numerous improvements over this simple type. However, the basic principle remain the same. Next topic is optical activity and chemical constitution. Optical activity is a purely constitutive property, that is, it depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which four different atoms or groups are attached. Such a carbon atom is called an asymmetric carbon atom and is usually shown by putting a sign of star over it. A very simple example of such a compound is that of lactic acid. It is found that such a compound exists in two forms, one of which the one of which rotates the plane of the polarized light to the right and is called dextrorotatory, and other which rotates the plane of polarized light to the left and is called levorotatory. The two forms have the same constitution. Thus, the two forms of space isomers are called optical isomers. Lebel and Van 't Hoff pointed out the differences in the two forms by suggesting that in case of such molecules, the asymmetric carbon atom is present in the center of a regular tetrahedron, and the four atoms or groups attached to it are present at the corners of the tetrahedron. This gives rise to two different spatial arrangements which were like the mirror image of each other. These mirror images are different in the sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of the same person. These are the two forms given, which shows the spatial arrangement. In form first, the arrangement of H to OH is clockwise, and in form second, the arrangement from H to OH is anticlockwise. Hence, if one of them is dextrorotatory, then other is levorotatory. However, by inspection of the configurations, it is not possible to predict as to which form is dextro or levo. The two forms are said to be enantiomorphs. Further, if equimolar quantities of two forms are mixed together, a third form is obtained which is optically inactive. This is obviously due to the fact that the rotation caused by one form to the right is nullified by the equal rotation caused by the second form to the left. This process is called external compensation, and the substances thus obtained are called racemic mixtures. This form can be separated into D and L forms by suitable methods. In case of compounds containing two asymmetric carbon atoms, example tartaric acid, a fourth form is also found to exist. In this form, the rotation caused by half of the molecule is compensated by the other half within the molecule. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may be mentioned that optically activity is found not only in the organic compounds containing an asymmetric carbon atom, but also in the compound which contain other asymmetric atom like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compound may not contain an asymmetric atom but are optically active because the molecule as a whole is asymmetric. Thus, it may be calculated that the optical activity is a property related with asymmetry of the molecule. Hence, optical activity can be used to test the presence of asymmetry in the molecules. These are some examples and numericals given. Next is dipole moment. General introduction of dipole moment. Polar and non-polar covalent bond. A covalent bond is formed by the mutual sharing of electrons between two atoms. If the two atoms are identical, example hydrogen, chlorine, etc., the shared pair of electron is attracted equally by both the atoms, and hence it remains exactly in the center of the two atoms. Thus, neither of two atoms in such molecules acquire positive or negative charge. The bond thus formed between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example HCl, in HCl molecule, chlorine atom is more electronegative than the hydrogen atom. Hence, the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electron is more displaced towards the chlorine atom than towards hydrogen atom. As a result, the chlorine and the chloronic end of the molecule acquire a slight negative charge, while the hydrogen end of the molecule acquire a slight positive charge. The bond thus formed between the two dissimilar atoms is called polar covalent bond, and the molecule is called a dipole because it has developed positive and negative poles. Thus, the situation in HCl may be represented as shown: del positive charge on H and del negative charge on Cl. Next, dipole moment of a diatomic molecule. The extent of polarity of a molecule is expressed in terms of dipole moment, which is defined as the dipole moment of a polar diatomic molecule is the product of the charge on each end of the molecule and the average distance between the centers of their nuclei, that is the bond length. In general, for a polar diatomic molecule AB, in which atom B is more electronegative than A, if plus Q is the charge on the end A and minus Q on the end B of the molecule, and D is the average distance between the centers of their nuclei, then the dipole moment of the molecule AB is given as mu is equal to Q into D. Obviously, if the molecule is non-polar, then Q will be 0 and hence mu equal to 0. Next is units of dipole moment. The charge present on the ends of the dipole moment is usually of the order of 10 raised to power minus 10 ESU, and the distance between the atoms is usually of the order 10 raised to power minus 8 centimeter. Therefore, mu must be of the order 10 raised to power minus 18 ESU centimeter. This value is called 1 dBi. Thus, 1 dBi is equal to 10 raised to power minus 18 ESU centimeter. Next is vector nature of the dipole moment. The dipole moment is a vector quantity, that is, it has both distance and direction. Next is electrical polarization of molecules. Every molecule is made up of a positively charged nuclei and negatively charged electron cloud. The center of the positive charge coincides with the center of the negative charge. Hence, when such a molecule is introduced between the two plates of an electric field, the positively charged nuclei and hence the center of the positive charge is attracted towards the negative plate, whereas the negatively charged electron cloud is attracted towards the positive plate of the electric field. As a result, the molecule gets distorted. This is called polarization of the molecule, and the distorted molecule with positive and negative ends is called an electric dipole. The molecule remains polarized so long as the electric field is applied, but goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole formed is called induced dipole. Since even after polarization, the molecule is neutral as a whole, this means that the positive charge on one and must be equal to the negative charge on the another. Suppose this charge is q. If d is the distance of separation between the charges, then dipole moment of the induced dipole will be given as mu I is equal to q into d. Let it be equation first. Evidently, the value of mu I will depend upon the nature of the molecule and the strength of the electric field, say x. We write mu I is equal to x greater than capital X, where x is a constant and is called polarizability of the given molecule. Let it be called equation 2. X is further found to be related to the dielectric constant d of the medium present between the plates, that is, molecules being studied, according to equations put forward by Clausius and Moissotti. D minus 1 divided by d plus 2 into m rho I is equal to 4 by 3 pi n kx. Let it be called equation 3, where m is molecular mass of the molecule, Rho is the density of the molecule and n is the Avogadro's number. Next is Clausius-Mosotty equation. Suppose an electrostatic field is applied to the plates so that they are charged. Suppose the strength of the uniform electric field produced between them is E naught. Now, if a non-polar medium is placed between the plates, the strength of the electric field will be reduced to E because the induced dipole act in opposition to the applied field and hence partially neutralize the charge of the plates. The ratio E naught by E is called dielectric constant D of the medium. From electrostatics, it can be shown that E naught is equal to E plus 4 pi I, where I is the induced dipole moment per unit volume, that is I is equal to mu I into N, where mu I is induced dipole moment in a single molecule and N is the number of molecule per cc. The intensity of the electric field strength X acting on each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of the molecule but small in comparison with the distance between the plates. The electric intensity X is then made up of the following parts. First, the field strength of the charges on the plate, that is E naught. Second, the charges induced on the surface of the dielectrics in contact with the plate, that will be equal to minus 4 pi I. Next is the charge induced on the surface of the spherical cavity, that is 4 by 3 pi I. So we can say that X is equal to E naught plus 4 by 3 pi I minus 4 pi I. Further, we can write it as X is equal to E plus 4 pi I plus 4 by 3 pi I minus 4 pi I. So this is the complete derivation. The final Clausius-Mosotty equation is Pi or Pd is equal to d minus 1 divided by d plus 2 into m divided by rho. This is the final equation. Next is effect of temperature on polarization. Using Mosotty-Clausius equation, the value of molar polarization have been determined for a number of substances. It is found that whereas molar polarization of number of substances such as O2, CO2, N2 and CH4 are constant and independent of temperature, the polarization values for some other substances such as HCl, CHCl3, C6H5NO2 and CH3Cl do not come out to be constant but decreases with increase of temperature. This observation has been the basis of the measurement of dipole moment and the study of molecular structure as explained below. In case of molecules such as HCl, CHCl3, etc., their centers of positive and negative charge do not coincide with each other. Thus, they possess some dipole moment even in the absence of electric field. The dipole moment thus possessed by the molecule is called permanent dipole moment. In the absence of electric field, these permanent dipoles are oriented in a random manner due to thermal agitation. However, in the presence of an electric field, two disturbing effects will take place. These are the electric field will tend to rotate and orient this dipole in the direction of the field, and the electric field will tend to polarize the molecule. If the molecule were stationary, the dipole would have been oriented perfectly parallel to the electric field, that is at right angle to the plates of the electric field. However, due to thermal agitation, they take up position in between that of the original state and the perfectly parallel state. Thus, in case of molecule possessing permanent dipole, the right hand side of Clausius-Mosotty equation will give the total polarization Pi, which will be the sum of the induced molar polarization and the orientation molar polarization, that is Po. Next is measurement of dipole moment. First, vapor temperature method. We can use the equation Pi is equal to A plus B divided by T, where A is equal to 4 by 3 pi n alpha and B is equal to 4 pi n mu square divided by 9k are constant for the given substance. The equation is primarily applicable to gases and vapors. Thus, if Pi is plotted against 1 by T, a straight line graph will be obtained if the molecule possessed permanent dipole. The slope of the dipole plot will be given by B is equal to 4 pi n mu square by 9k. From this equation, the permanent dipole mu of the molecule can be calculated, as all other quantities are constant whose values are known. The straight line plot for a few substance with and without permanent dipole are present. It may be seen that whereas Pi varies with temperature for HCl, CHCl3, etc., possessing permanent dipole, there is no effect of temperature on substances like CH4, CCl4, etc., which do not have permanent dipole and hence possesses only induced molar polarization. Method of measurement of dipole moment. As explained above, the basic equation for the determination of dipole moment is Pt is equal to d minus 1 divided by d plus 2 into m divided by rho is equal to a plus b divided by t, where a and b are constant, with b is equal to 4 pi n mu square divided by 9k. Thus, the experiment involved the determination of the dielectric constant d and the density rho at different temperatures T. The value of Pt are then calculated and plotted against 1 by T. If Pt is found to vary linearly with 1 by T, the substance possesses a permanent dipole moment, and the value of the dipole moment is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment, that is, it is nonpolar. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in vacuum between the plates CO and then measuring the capacity of the same condenser when filled with the given substance C. The dielectric constant of the given substance is then given by D is equal to C upon C naught. Second method to measure dipole moment is refraction method. According to Clausius-Mosotty equation, the induced or distortion molar polarization of the molecule is given by Pi or Pd is equal to d minus 1 divided by d plus 2 into m divided by rho is equal to 4 by 3 pi n alpha. As d, that is dielectric constant, is a pure number, molar polarization P is simply molar volume of the material. Further, it has already been explained that it is independent of temperature if the substance is non-polar and does not have a permanent dipole moment. For such molecule, it was derived by J.C. Maxwell that the dielectric constant of a substance is related to its refractive index for light of long wavelength according to the equation D is equal to n limit tends from infinity to 2. To find total value of Pd, it is therefore necessary to measure the refractive index using infrared rays because they can displace the heavy atomic nuclei as well as electron, but measurement of refractive index and infrared radiation is difficult. Hence, the problem is solved by finding electron polarization by measuring the refractive index using visible light. So this is the derivation. So this is all for today's video. In next video we will discuss another methods for the measurement of dipole moment, which are dilute solution method, and after that dipole moment and chemical constitution. This is all for today's video. Thank you all for watching.